on example 5, let f of x equal to the piecewise function x squared if x is less than 1 and negative x plus 2 if x is greater than or equal to 1. And we have a nice nifty little graph there for us. And the question asks us to find the limit as x approaches 1 f of x if it indeed exists. So when you have yourself a piecewise function, if you're evaluating the limit at its breaking point, you definitely want to break this up into its left side and its right side limits. It's one-sided limits. That's what we're going to do right here. So I'm going to make some sort of note to indicate that we need to use one-sided limits. Okay, so let's take, now if you look at the individual parts, like that's polynomial and this is polynomial. So by that previous law, we're allowed to directly substitute it in. But things get a little bit more complicated based on the fact that we have divided our function up into two parts, two pieces. So individually, I want to take the limit as x approaches 1 from the left-hand side of f of x, and the limit as x approaches 1 from the right-hand side. So the left side is the part that's where x is less than 1. So maybe I make some sort of note that this one is the left, which makes this one here the right, because it's where x is greater than or equal to negative 1. Okay, so we don't actually care what the function is equal to at 1. It's just on the left side and the right side we want to see what that's equal to. So this is the same thing as the limit as x approaches 1 from the left of just x squared. X squared, we're totally allowed to directly substitute that in there, and that is equal to 1. Okay, and then on the right-hand side, that should be the same thing as the limit as x approaches 1 from the right of negative x plus 2. And again, that's polynomial, so we're totally allowed to just directly substitute that in there. Negative 1 plus 2 is equal to 1. And notice that both of these numbers are identical. So we are approaching the number 1 from both sides. Therefore, the limit exists. Not only does it exist, it's equal to 1. So therefore, the limit as x approaches 1 of f of x is in fact equal to 1. Now, we can confirm that with a graph, of course. We can see that on the left side it's approaching 1, and on the right side it's approaching 1. We have this sharp turn here, but that doesn't prevent the limit from existing. On the follow-up question, notice that the, let's see, did the function change a little bit? Oh, it sure did. So we have a little minus sign there instead of a plus sign. And of course the graph would be different, but we don't even have access to the graph. Let's see how this limit now changes. Again, whenever I have a piecewise function, if we're trying to evaluate the limit at the point at which it breaks, then we're going to have to use some one-sided limits. So I'm going to break this up as the limit, how about our blue crayon, the limit as x approaches 1 from the left of f of x. And once again, the left is going to be where x is equal to or less than 1, so it's the top portion here. So this is equal to the limit as x approaches 1 from the left of just x squared. It's polynomial. You can plug it in and you just get 1. Nice. So let's try the same thing from the other side, limit as x approaches 1 from the right. And on the right side, that is the bottom piece where x is greater than or equal to 1. That's the same thing as x, the limit as x approaches 1 from the right of negative x minus 2. And this time, whenever I plug in 1, I'd have negative 1 minus 2 is negative 3. And I can see that my two numbers here are different. On the left side and the right side, they are different. And I can conclude that the limit here does not exist due to differing left-right behavior. So therefore, the limit as x approaches 1 of f of x d and e due to differing left-right behavior. Which brings us to a slide that we've seen before about the existence of a limit, where we're saying that the limit exists if and only if the limit from the left and the limit from the right are the same exact number.